Welcome to today's Explainer. We're jumping right into a really fascinating technical stack today, an intelligent, AR-driven wound management system. We're going to figure out exactly how computer vision, deep learning, and augmented reality all come together to solve a massive, real-world clinical challenge in elderly care. So, for all the IT experts, software architects, and tech enthusiasts tuning in, we're going to explore this architecture from the ground up. We're talking neural networks, image processing, and the AR integration that actually makes this whole thing possible.
Okay, let's dive into this. Here is our technical roadmap for today. We'll start with the system architecture, move into image pre-processing, explore the UNet DeepSkin AI model, look at the AR visualizer, and then wrap things up with enterprise integration.
All right, kicking things off with Section 1, System Architecture Overview.
To solve the challenge of monitoring chronic wounds in elderly care, which honestly has traditionally relied on a lot of guesswork, this system relies on a very strict digital pipeline. First up, it starts at a mobile user interface where caregivers actually capture the images. That data then hits the pre-processing module to clean the inputs, which feeds directly into the AI engine for tissue segmentation. From there, the processed data is instantly pushed back into an AR visualizer right on the device. And finally, the whole shebang syncs up to a secure cloud backend that uses encryption and strict access protocols to ensure full HIPAA and GDPR compliance.
Moving right along to Section 2, Image Preparation and Augmentation.
Now, any data scientist will tell you that a model is really only as good as the data it ingests, right? And in clinical environments, you absolutely cannot control the lighting or the camera quality. To handle this messiness, the pipeline starts with brightness normalization and noise reduction. But crucially, it uses edge-preserving smoothing. This is a neat trick. It removes the noise while keeping the sharp, defining boundaries of the wound perfectly intact. Plus, during training, the dataset is artificially expanded. They use augmentation techniques like rotation, flipping, and injecting Gaussian noise. This forces the model to learn actual tissue features rather than just, memorizing perfect photos.
Which brings us to Section 3, the DeepSkin Engine and the UNet architecture.
So, it turns out the core computer vision task at play here is called semantic segmentation. Unlike basic object detection, which basically just draws a clunky bounding box around a wound, this assigns a specific class label to every single pixel in the image. It's literally a pixel-perfect map. This allows the AI to perfectly trace those highly irregular boundaries that separate complex tissue from healthy skin.
And this brilliantly illustrates how they achieve that semantic segmentation. The engine utilizes a custom implementation of a UNet architecture. Now, UNet is pretty famous in medical imaging for its U-shape. It features an encoder that compresses the image to figure out the what, and a decoder that expands it back up to figure out the where. But the real power of its design is that the UNet utilizes skip connections. These connections bypass the deepest layers of the network. They take high-resolution, localized details from the encoder and feed them directly over to the decoder. This means the network doesn't lose those fine, localized details during the compression process, which is exactly what allows for such incredibly precise boundary mapping.
Looking at how this handles real medical data is just fascinating. Wound tissues aren't conveniently distributed, are they? You might have this massive area of healthy granulating tissue, but then a tiny, incredibly dangerous spot of necrotic tissue. To prevent the AI from just ignoring that tiny spot to cheat and get a high overall accuracy score, the system uses a weighted categorical cross-entropy loss function. This specifically penalizes misses on those critical, smaller areas. Optimized with the Atom optimizer and paired with the dice coefficient, it essentially forces extreme segmentation precision.
And the results? Well, when evaluated against thousands of pixel-wise annotated samples, the model achieved highly impressive tissue classification accuracy. It hit 91.4% accuracy for granulating tissue, 89.2% for necrotic tissue, and 87.9% for epithelizing tissue. Being able to segment these distinct clinical types so reliably gives caregivers a seriously solid foundation for treatment. It provides a real objective baseline to actually monitor patient progress over time.
All right, let's look at the presentation layer in Section 4, AR overlays for elderly care.
Because here's the thing. Having a highly accurate AI is great, but it absolutely has to be useful right there at the bedside. Historically, caregivers relied on manual inspections and, literally, holding up physical paper rulers next to a patient, which, as you can imagine, is about as subjective and error-prone as it sounds. This new approach leverages frameworks like ARCore and ARKit to superimpose real-time, automated boundaries directly onto the camera feed. It completely removes the guesswork.
The technical execution here is absolutely vital. The on-device inference happens incredibly fast. We're talking under 3 seconds. This enables live wound area indicators to float seamlessly over the patient's skin in real time. The system projects virtual rulers that dynamically adjust as you move, and they boast a measurement error margin of less than 5% compared to manual measurements. Plus, all of this highly complex technology is wrapped up in a super accessible UI tailored specifically for aged care environments. It features large fonts and clear visual cues so that even non-expert caregivers can easily navigate the tool.
So the crucial point is this. All of this advanced deep learning, the UNet architecture, the edge-preserving smoothing, it all leads to this single human metric. In usability tests, 92% of caregivers in aged care homes reported that this application improved their confidence in wound monitoring. By standardizing the documentation and visualizing the data directly in their line of sight, the technology directly empowers the frontline staff who need it the most.
Finally, let's zoom out a bit for Section 5, Future Scope and Enterprise Integration.
To truly transform healthcare, a system like this can't just live in a silo on a standalone device. Here's the technical roadmap going forward. We're currently at the AR overlay stage. The short-term goal is Seamless Electronic Health Record, or EHR. This syncs the wound data directly to a patient's central file, making longitudinal tracking absolutely effortless for remote clinicians and telemedicine. Looking midterm, the roadmap points to 3D LiDAR modeling. By utilizing the depth sensors on modern tablets, the system will move way beyond 2D area calculations to capture incredibly precise 3D volume estimations of the wound crater. And long-term, it culminates in machine learning progress prediction, basically recommending proactive interventions before a wound even has the chance to get worse.
So I want to leave you with this question to ponder. How will seamless EHR integration and predictive AI further transform remote clinical monitoring? We're literally moving from reactive, manual medicine into a whole new era of proactive, visually augmented healthcare. Thank you so much for joining me today to figure out the technology that's shaping the future of care. Keep learning, keep building, and I'll catch you in the next explainer.